Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I will talk about convergence criteria and finite element analysis using ANSYS mechanical APDL. Actually, in ANSYS or mechanical APDL, when you are following finite element method, trying to reach towards perfect solution, and the perfect solution is achievable when discretization is perfect. Let's start it. So before starting this model, we have to create a desktop folder by the name of ANSYS, and all work will be set there itself, right? Okay. Now we are opening mechanical APDL. First of all, you have to, from the file, you have to start change the directory. So all the works, what will be done, that will be set in the folder what we have created before in the desktop. We are going to the folder by the name of ANSYS, and all works will be saved there in the folder ANSYS, right? Okay. Next one, we have to change the title of this job. File, change title. Let's find the name of the title as convergence criteria. We will give the name as convergence criteria, and that will be showing in the lower left corner of the screen. As we cannot see it, to see this name change, we can go for plot replot. It will show convergence criteria. Okay, right, it's showing that. Now, starting from preferences, it will move from top to bottom from the left hand side. Starting from preferences right now, there is structural analysis, static structural analysis. Okay. Next part, we will start from preprocessing. We have to select the element type. Nothing is different, so we have to add the element. Adding the element. Now, here we will select solid element, and by default it is taken word 4 node 182. Okay, and element reference number is 1. Okay. Okay. Next part, we have to select this problem. We have to consider this problem as a plane stress problem. So what we have to do is plane stress with thickness. Okay, close. Next, we have to provide the thickness values. That will come from real constants. Real constants, add init del, add. Okay, now it is asking thickness. Thickness, let's provide the thickness equal to 10 millimeter. Okay, done. Next part is material properties. We have to apply the material models, structural, linear, elastic, isotropic. Isotropic means in all directions material property will not change, it is constant, right? And EX means modulus of necessity. We are taking still, so the modulus of property will be 2E5. And Poisson's ratio 0.3. Okay. Now, next part is we have to start modeling. Now, in ANSYS mechanical APDL, modeling is not that much of popular. So, what actually is done is we are modeling in different CAD softwares and exporting with IGS format. While drawing these things, we have to get a very good idea about like coordinate geometry. So we have to draw in 2D plane coordinate geometry systems, right? So first of all, we have to create two concentric circles. That will be coming under areas and circles. Angular circles will be the two concentric circles will be required, and here we have to follow coordinate geometry system. X and Y is like origin. So in this case, we will provide 0, 0, or if we don't provide, by default it will take 0, 0. Radius 1. We are considering the radius 1 as the big one with 60 millimeter, and radius 2 as 40 millimeter. apply. 2 concentric cycles have been made. Now another 2 will made some distance away at 200 millimeter distance away, right? So see right now, again x and y coordinate to see at a distance of 200 millimeter away, so x will be 200 millimeter. Y will not change, it will be the same plane, and radius of that one, let's say, is 40 millimeter and 25 millimeter radius. Okay, we have done 2 concentric cycles. Now in between this one, we have to provide one rectangle. Then finally we will provide some fillets, right? So next part is you have to provide areas again. That will be rectangle by 2 corners. Here also x and y is the coordinate of the location of the rectangle. We start from where some point anywhere in between this rectangular in this circular portion, angular circular portion, right? So let's provide the x value equal to 50. As the radius is 40 to 60, so 50 will be in between here itself. So for drawing the rectangle, you have to come to this position here itself, somewhere else. So you have to come down a little bit, minus y coordinate, minus, maybe you will take this one 20 down, and width of the rectangle, let's take that one 120 mm, and height will be 40. Okay, the cycle is done, the rectangle part is done. Now we have to draw some, here at some kind of fillet will be required. Before that, we are having 3 different areas that will be connected as a single area. That can be done using this operate booleans, add areas. Now we have to add all these 3 areas. How to do this one? Pick all. That means it is now a single area, right? Next part, we have to provide fillets at all these boundaries, lines, line fillet, this line, that line, apply. These 21 and 26 are line numbers, and fillet radius, it is a singlet. Provide the fillet radius equal to 40 millimeter first. Apply. Is done. Now we should provide here itself again. Apply. By default it is taking 40. Apply. 2 fillets have been done. Now add this part also to be required. Select this one, that one. Apply. This part will provide a little less fillet. Let's take that one for 20 mm. Apply. And again here. Okay. 20 mm. Okay. We got this fillet lines. Now these lines are actually empty. We have to fill these areas. So again, areas arbitrary by lines. We have to fill these areas. So select the lines, area will be filled up. Apply. This area is filled up. Again, down part also we have to do the same thing. Select lines. Apply. Again, top part also here. This one, that one, this one, all 3 lines selected. Apply. Now this part, this one, this one, this one. Okay. All these lines. Now these areas what we have created, these are actually not connected with the main areas. That will be connected. So we can connect it by operate booleans, add areas. Now we can separately select these areas or directly from pick all will be selected. Now it is a single object. We got the object, right? Now we have to go for meshing, right? Here comes the convergence criteria actually. We have to go for different types of different size of meshing and see the answer how it is varying. Now when the answer will be constant with further meshing, then we see that convergence criteria is achieved, right? Okay. Starting from machine. Here for meshing, different options are available. You can go for mesh tools, that is easiest one, but we are selecting different sizes of the meshes. Manually we'll select the different sizes. So we'll go for size controls, manual size, areas, and all areas. It is asking the meshing size, it is asking, right? Manually you can provide to achieve the convergence criteria. We'll take different sizes of elements and see how the answer is varying with different sizes. And at a particular value of mesh area, the answer will be constant, it will not change. That is actually convergence criteria, right? When with further meshing, the answer is not changing, the result is not changing. That means convergence is achieved. We'll see this one right now. Initially, let's take the element size equal to 10 millimeter. Okay, done. Now that to be meshed, mesh areas, free, can pick one or select the object. Okay, meshing is done, right? This is meshing. This is very rough meshing, not fine one, coarse meshing. Let's see the answer of this one. What to do is to apply boundary condition right now. We'll come from solution, analysis type, new analysis. It is static structural analysis. Then define loads. Apply structural displacement on lines. As it is a plane stress problem, it is considered as a line only. It is a 2D problem right now. Plane stress problem is 3D problem is converted to 2D problem, and thickness is provided. Structural displacement on lines. We are planning to fix the right hand side fixed. So this part has 4 quadrants. These lines are selected. Okay, and all degrees of freedom. It is x, y, z, all directions. The displacement we are providing 0. If you don't provide, by default it will take 0 value. So all degrees of freedom, the right hand side is having 0 displacement. Okay, that means right hand part is fixed. Now we have to apply pressure on the left hand side. It will come from pressure on lines. Again we will select the 4 quadrants, second, third, 4th quadrant selected. Okay, let's provide the value of our pressure equal to 50 megapascal. 50 megapascal pressure is applied, is going towards outer side. From inner side to outer side, pressure is applied. Next part, we have to go for solution. Solve current LS. If everything is fine, it will show solution is done. It is showing solution is done, so it is perfect. Now you can see the results, right? It will come from general post-processing. Now we can see a lot of things, lot of answers like displacement, stress, strain. Our task is to see the stress values only, because we are bothered about only convergence criteria. That means at which particular mesh size or element size the final answer is not changing, and the stress value is not changing. That one we are expecting to see. So we can see the results, plot results. Then to plot nodal solution, stress, and one with stress. It's showing that one with stress is maximum is at the red portion, right? And the value of maximum one with stress is 159.4 at element size is 10 millimeter. We can write down this one. We can save this part, but control, capture image, file, save as. We'll save this one in the directory what we created before. In the desktop, the folder name is ANSYS. They will save it as the name of stress at 10 millimeter size, millimeter mesh. We'll save this part, close it. The answer is 141. We can remember this point. Okay. It's the same thing you can see by listing also, like list results, nodal solution, stress, one means stress. Okay, it will show thousands of results, and the maximum one to see. Maximum is showing 159 megapascal at node number 83. Okay, this part also you can save it. File save as stress at 10 mm size. Okay, what was the value before we got to plotting? We'll see again. Plotting, nodal solution, stress value. Again, it was 159. Both cases, it is having same thing, right? Plotting and listing will same thing. Plotting will show in the graphical view, and listing it will provide in the form of numbers only, right? As it is a two-dimensional problem, initially it was 3D, but we converted it in 2D as a plane stress problem, right? We can see this model as a 3D view also. How to see? But controls, style, size and shape, and here display of element is off. We have to make it on. Okay. Now it is converted to 3D problem. Let's see. This is 3D problem with thickness equal to 10 mm, right? This is a 3D one, right? You can see perfectly. Now we can check the value of stress at different position different, and which point the stress is maximum. That one also we can find out. We'll show this one at the final stage only, right? And now, as we are concerned about stress only, we'll go back to the 2D drawing again, front view, and we convert to 2D again. But controls, style, size and shape, display of element should be off again. Okay, now this 2D problem converted. Okay. Next part is we have to change the mesh size again, right? How will we do it? We'll go back to plot elements with mesh size. You can show the previous mesh size. That mesh size will remove it, and we'll go for further meshing. Meshing. We'll clear the areas. Select all or pick all. No areas applicable here. So next part, plot areas again. Can do the areas, right? Now we have to remesh it again. So going for mesh, size controls, manual size, areas, all areas. Initial length of mesh was 10 mm. Now we are planning to mesh size as 5 mm. Okay. Mesh, areas, free areas. You can pick all or select the object. Okay. Mesh is done. Now it is little bit final mesh you can see. Okay. We'll check the answer again. So meshing is complete. Now we have to apply for boundary conditions. We come from solutions, analysis type, new analysis, which is static structural analysis, define load, apply structural displacement on lines. What we'll do, right part, we have to fix it. 4 lines or 4 quadrants, you have to fix it. Okay, and displacement of all these quadrants will be 0. All degrees of freedom is selected, and this is 0 value. By default, it is saying 0 value. Okay, that is right part is fixed. Now, left hand side cylindrical portion of the lines, you have to apply pressure. Pressure on lines. Select the 4 quadrants again. 2, 3, 4. Okay, and the pressure is 50 megapascal. Okay. Now we have to solve it. Solve current LS. Okay, if everything is right, it will show solution is done. Okay, close it. Let's get the results again. general processing, control plot, nodal solution, stress, and here boundary stress. You see this 170, initially it was 159, it is changing, right, at different size. So we can say that convergence criteria is not achieved yet. Initially it was 159, now the maximum stress is 170. Okay, so again we have to remesh with further fine mesh is required. It will come from preprocessor, meshing, then size controls. Before size control, we have to create these areas, right? So first of all, plot elements. They showing the meshes. This mesh we have to remove it by clearing this, right? Clear areas. Pick all areas are cleared, then plot areas. We have to drawing as in the previous case, initial case, now we have to mesh it. Size controls, areas, all areas, size we are providing. Initially it was 5, no? Initially it was 10, then we got 5. Next part we have to make it maybe 2 mm or 2.5 mm, half of that. Okay, mesh areas free, select it, okay. Meshing is going on now. Further, fine mesh you can see it's very fine mesh right now, right? You can see the view is very fine mesh. It's 2.5 mm length of each size. That means different elements are found with length equal to 2.5 mm, right? Again, we have to apply boundary conditions, force, pressure, etc. So, starting from again, solution analysis type, new analysis, static structural analysis, define loads, apply structural displacement on lines, select the 4 quadrants of right hand side. Okay, and all degrees of freedom should be having 0 displacement. Okay, that part is fixed. Finally, you have to apply pressure on the left hand side, pressure on lines, take the 4 quadrants. Okay, and the value of pressure is 50 megapascal. Okay, done. Now solve it. Solve continuous. Okay, solution is done. Everything is perfect. To get the results right now from general post-processing. Control plot, nodal solution, stress, and here boundary stress is coming. Yeah, right, 175. Can remember the previous case at mesh size 5 it was 170. Now it is 175, right? 175 at mesh number. Mesh size is 2.5 mm. This part also you can save it. But controls. Capture image, file, save as. Then note down stress at 2.5 mm. In mesh size. The value is 175. It's changing. Initially it was 159, then 170, 170 is changing one by one. Right? Again, you have to do the same thing. Still we get the same value with further meshing going. This area is stress is not changing. That is our requirement. So again, plot elements. The mesh should be cleared. We come from preprocessor, meshing, clear areas. pick all areas cleared, then plot areas again. This is done. Next we have to select mesh size. You come from search controls, manual size, areas, all areas, mesh size. Next we can provide the mesh size equal to 1 millimeter. Let's provide 1 millimeter. Then mesh areas free, select the object, OK. Meshing is going on right now. As finer meshing will be there, so it will take some time. Okay, done. You can see the mesh size. It is very perfect. Very fine mesh is going on there. Very fine mesh. Like this, mesh size is 1 millimeter. Very fine mesh you can see here, right? Okay. Now see, last answer how much it was, we can see again. Last answer was from desktop, you can see at 2.5 millimeter. The answer was 175. We can recall this. Before how much it was? 175. Okay. Now our task is to the same thing again. We have to apply boundary conditions and apply force, pressure, etc. So we are applying now solution analysis tab, new analysis. It is static structural analysis, define loads, apply structural displacement on lines. But select the rightmost part of the connecting rod to be in the form of quadrants, 4 quadrants selected. OK, and all degrees of freedom with 0 displacement. Right part is fixed. Now pressure on the left hand side. On lines, 4 quadrants to be selected. OK, and value of pressure is 50 megapascal. OK, done. Now to solve it. Solve current LS. Okay, solution is done, everything is perfect. We'll get the results in post processing, general post processing, right? So plot results, can do plot, nodal solution, stress, 1 minute stress. Let's see, it is 178, again it is changing, so it is approaching towards the convergence criteria. So plot controls, capture image, file, save as, stress at 1 millimeter size, 1 millimeter mesh. The answer is 178, 1 millimeter, right? Okay. Now we'll go for 0.5 millimeter mesh size. Let's see what happens. So we are changing the mesh size. First of all, we have to create elements. Elements means we are seeing very fine mesh size with small elements, right? Okay. Next part, we have to remove these areas. It will come from preprocessor, meshing, clear areas. Pick all areas are cleared. Now plot areas. We get the object again. Areas we can see. Now meshing to be done. Size controls, manual size, areas, all areas. It was 1 millimeter, so we have to go to 0.5. Okay. Now mesh areas free. Select the object. Okay. Now mesh is being generated. Very fine mesh of 0.5 millimeter length. It will take some time as it is producing final very fine mesh. And we can recall the previous answer, it was how much it was. Let's see. Previous answer was as 1 millimeter stress was 178 was the last stress, right? 178.5 megapascal, 178.5. Still meshing is going on. Very fine meshes are being generated. Okay, fine, done. Right? We'll see the machine. How very fine mesh is generated, you can see by zoom. You can see very fine mesh is being generated, right? Very fine mesh. Okay. So you see, we have to apply the boundary conditions right now. Meshing is done, so we are starting from solutions. Solutions, analysis type, new analysis. It is static structural analysis, then define loads, structure and displacement on lines. Right? This is zoomed out, we have to remove it. We have to make it small. By zooming, we can make it small. Okay. We have to select the 4 quadrants. First, second, third, fourth. Okay. Already gives a freedom with 0 displacement. Okay, that right part is fixed. Now we have to apply pressure on the left hand side. Pressure on lines. Select 4 quadrants. First, second, third, fourth. Okay. And the pressure that is 50 megapascal. Okay. Pressure is applied. Now we have to run it. So solve. Solve currently is okay. It's solving. It will take some time. Okay, solution is done. Fine. Close it. So we have to see the results through general processing. Plot results. Continue plot. Nodal solution. Stress. 1 meter stress. Let's see. 178.86. We'll save it. I think we got the convergence criteria. Before it was how much? 178.5. I think. We'll see it. What controls? Capture image. File. Save as. Stress at 0.5 millimeter mesh. How much is the answer? 178. We'll go back to the previous answer and see whether convergence criteria is achieved or not, right? You see the previous value, 178.86 is present value. So we'll go back at 1 millimeter. Yeah, it was 178.5. So we can say that convergence criteria is achieved. With further meshing, the final answer is not changing that much. So this is all about convergence criteria. That means with further meshing, the final answer is not changing. Now, one thing we can do, we can check at which point the stress is maximum, because red portion, lot of area is red portion, right? Let's see how can we see it. We'll do one thing, like we have to see the node numbers. By listing, we can check at which node the stress value is maximum. So list results, nodal solution, stress, 1 meter stress, will show thousands of results, and we want to see the last one, that is maximum stress at 178.89 at node number 1766. We have to remember this one. We have to find this node number 1766. So save this part. File, save as, stress at 0.5 milli mesh. Save it. The node number is 1766. That will find out, right? We'll do it right now. How to do this one? We have to provide the numbers of these meshes. So plot these are all nodes. This is showing all nodes, right? We are concerned about this position only. So what can we do is by zooming you can see this part, and also node numbers here that we check. All these are nodes, right? What can we do is plot controls, pan zoom rotate. You can go for box zoom. We're concerned about this area only because here is maximum stresses, right? These are the different nodes, and we can remember the node number 1766, the node number. At that position, the stress value is maximum. So what to do is plot numbers right now. Plot numbers. Numbering of node numbers should be on. Node numbers, we should make it on. Okay. Now we can view node numbers. These are the node numbers. Our point of discussion is 1766. This part. So this part is having maximum stress number, right? We can go back to the answer. What it was before, we saw that. Let's see the answer. It is in listing we saw stress at 0.5 millimeter, right? This was the answer. You can open it through Notepad. It was showing, it is showing thousands of answers. The last part was the maximum value of stress is 178.189 at mesh number as node number at node number 1766. That is, at this point stress is 178.89, 1766, right? We'll show this one 1766. That is, this is the point where the stress is maximum. Okay. So what did we understand from here? We understood that convergence criteria means at a different node size or different mesh size, the final answer of stress or displacement, whatever, final answer will vary. So when with further subdivision or further discretization of meshes, if the mesh size is changing, what we find is, if with further discretization or further meshing, if the answer or solution is not changing, then we can conclude that our convergence criteria is achieved, right? Okay. So what we'll do, we'll go back to the previous things again. Plot. We can close this numbering also. Plot controls. Numbering will make it off. Okay. And here also plot elements. This is the elements. These are the elements. This is the final one, right? Okay. Thank you so much for watching this video. If you like, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much again for watching this video. Thank you.